All right, I just want to start by thanking Professor Girvin, Dr. Weiss, and Mr. Shasteen for all their teaching over the past month. And then starting with some. Let's see, oh, there we go. Okay. So first of all, why do we care about quantum computers, quantum computing, all of that? So using certain quantum properties, quantum computers have the potential to outperform classical computers with certain calculations. These properties are, for example, superposition, which allows for the simultaneous processing of a lot of information, and entanglement, which allows for a lot of connected calculations to occur at once. And then just some basics. So what is a qubit? So classical computers store information in bits of 0 and 1. So if a computer was simulating, for example, a light being on or off, you might have that the 1 bit means the light is on and the 0 bit means the light is off. But in the quantum world, bits are no longer just in the 0 or 1 state. They can be, but they can also be in a superposition of both states at once. So think Schrodinger's cat with the spool of the graphic over here, where before you open the box, the cat is simultaneously dead and alive. When you open the box, it's either dead or alive. Same thing with the qubit. Before you measure it, it can simultaneously be in 0 or 1. And then when you measure it, it collapses into the 0 or the 1 state. A bit more about qubits. So qubits can be in the 0 or the 1 state or a superposition of the 2, where this notation is called Dirac notation. 0 and 1 with in this way are both column vectors, where 0 is 1, 0 and 1 is 0, 1. And these are the basis states of a two-dimensional Hilbert space, which is a vector space used for quantum mechanics. A quantum state describes the probability that a qubit will be in the 0 or 1 state when it is measured. And unlike seemingly probabilistic things in nature, this is generally probabilistic. So for example, if I flip a coin, there are things called hidden variables, which if I feed to a computer, the computer can predict whether the coin flip will be heads or tails. But with quantum mechanics, there are no hidden variables. There are no hidden variables, so it is generally probabilistic. The general state for a qubit that is in superposition is psi is equal to alpha on 0 plus beta on 1, where alpha squared is the probability that psi will be in state 0, and beta squared is the probability that psi will be in state 1. And then because the qubit has to either be in the 0 or 1 state when measured, alpha squared plus beta squared have to equal 1, meaning the state is normalized. The Pauli matrices are a set of matrices that are defined by Wolfgang Pauli, which are these sigma x, sigma y, and sigma z. And they're instrumental quantum mechanics. They're used for a lot of things like some basic gates and descriptions of qubit states. Now, gates are used to change the nature of the state of a qubit. There are a lot of different kinds of gates, some which act on one qubit, some which act on multiple qubits. Maybe the most basic gates are formed using the 3 Pauli matrices. They act on 1 qubit. The results are listed here, and they can all be calculated by multiplying the Pauli matrices by the 0 or 1 states as a column vector. So the X gate will swap the 0 state to the 1 state, and vice versa. The Y gate will take the 0 state to the I times the 1 state, and the 1 state to the minus I times the 0 state. And the Z gate will take the 0 state to the 0 state, and the 1 state to the minus 1 state, but not the minus 1 state. That's on state the minus of the 1 state. The Hadamard gate pictured over here, these are all coded with Qiskit. It'll take the 0 state to the plus state and the 1 state to the minus state, where the plus state is shown here, the minus state is shown here. And this gate is really important for things like entanglement because it allows you to take a qubit that is in just 1 state to a superposition of the states. On some multiple qubit gates, there's the controlled NOT gate, the controlled X gate, which applies the X gate to a target bit if the control bit is in 1. Where the control bit is shown by the filled-in circle. Q0 and Q1 are 2 different qubits, and the target bit is shown by the big circle with a plus in it. So here, for example, you had both qubits in the 0 state, nothing would happen. But if you had your Q0 in the 1 state, because it's in the 1 state, you'll flip your Q1, and so 1, 0 will go to 1, 1, and then the rest are all like that. And then another gate is a controlled Z gate, which will apply the Z gate to a target qubit if the control qubit isn't 1. So once again, here are the results, and that's the gate over there. And one more gate is the controlled Y gate, which applies the Y gate to a target bit if the control bit isn't 1. And on to some circuits. So the Bell circuit is over there. It's built with a Hadamard gate, and then it's followed by a CNOT gate, where both Q0 and Q1 are initialized to 0 or 1. In the 4 different ways to correspond to these 4 different states. So for example, in this first state over here, this is when Q0 and Q1 are both initialized to the 0 state. After you apply the Hadamard gate, taking your state to the plus state, and then you apply the C0 state, you then end up with this. If, for example, you were to switch Q0 to the 1 state, you would instead end up with this. These circuits create entangled qubits because you can't factor the final state. So you can't remove it, you can't take a state out and multiply it back in. So think it's like the states cannot be separated from each other. A unitary is a matrix which follows the rule U dagger U times U is equal to the identity matrix. So all the Pauli matrices are unitaries, and the Pauli matrices are also Hermitian matrices where U dagger is equal to U. And then if you tensor matrices which follow these properties together, they retain said properties. So for example, this circuit over here, which is built with a CZ gate, a C naught gate, and a CY gate, is also because each matrix in it is Hermitian and a unitary, the final combination is still Hermitian and a unitary. An exponentiation gadget, which is shown in this circuit over here. This one has a Hadamard gate followed by the unitary on the previous slide, followed by an X gate. It's an X theta gate. There's a rotation in it. Then there's another unitary gate, and then finally the Hadamard gate. And so what this does is if you have a state psi, normally with the unitary, you would result in U on psi. But in this case, you result in E raised to the power of I times state over 2 times U on psi. And the reason you would want this is because it this kind of thing allows you to create more complex gates in a restrictive environment. So for example, there are times when the way your qubits work, they have certain benefits like retaining information, but at the detriment where it is difficult to apply more complex gates. And this allows you to, using the more restrictive gates you might have access to, still apply a more complex thing to your qubits. The quantum oracle is so for example, the famous example is the Deutsch problem, where one wants to discover if a function is constant or balanced, where constant means for all the inputs, the outputs are the same, and balanced means for all the inputs, half the outputs are in state 1 and half the outputs are in state 0. And this is a problem which quantum computers can do more efficiently than a classical computer, because with a quantum computer, with a classical computer would take 2 questions, because you first would have to ask what is the function on the 0 bit, and you get the 1 bit, for example, and then you have to ask what is the function on the 1 bit, because if it's the 1 bit, it's constant, and if you get the 0 bit, it's balanced. But with a quantum oracle, you can you can determine whether your function is constant or balanced in only 1 question, because you can ask a question with information not on with information in a superposition, so with information on both the 0 bit and the 1 bit. So you can ask 1 question with twice as much information as you could on a classical computer, which allows you to answer the question with 1 question as opposed to 2. This is a bit confusing because you wouldn't actually know what the quantum circuit is or what the information is. You would just know what your question, what the answer to your question is. But this is kind of a bit of what could be going on behind the scenes with quantum oracle, where you could have a C naught gate with this information here, where Q0 stay the same throughout, and Q1 go to Q0 plus C naught Q1 mod 2. Oh, that's just